Today we are going to start this lesson on mandatory access control. Uh, Previously, we looked at discretionary access control as well as role-based access control. Today, we are going to look at mandatory access control. It's a pretty much different kind of access control mechanism compared to previously studied two access control models, and also there is a pretty difference in implementation as well, because most of these discretionary access control principles and role-based access control principles we are quite familiar, and we can see that they are being used quite often. But when it comes to mandatory access control, we don't see that model being implemented in a quite well, right? So it's being used in a very specific use cases. Therefore, we will not going to do any practical stuff related to this. Instead, we will be looking at this whole access control model as a conceptual, or maybe in a theoretical point of view. Right. So when that fails, that discretionary access fails. So discretionary access control is mainly about the ownership, who owns this object, so that the owner can decide the level of access or authorization, because the owner can grant the permission, or the privilege can be granted by the owner, and the owner can decide whenever the owner wants to revoke it, that privilege can be revoked. So discretionary access control is based on such a ownership-based model. So if we take a particular case where discretionary access control fails, this one we discussed earlier as well. One is so if we take a user creates a table and granting insert privilege to another user. So in this case, let's take user A creates a table P and grants permission to user B, and user A injects malicious code segment to user B's program code. So some of the data only accessible to user B will be inserted to table P. So I will repeat it again. User A is creating a table and grants insert permission to a different user, user B, and then user A inserts a malicious piece of code to user B's program. So some of the data only accessible to user B will be inserted to table P. So that's what this malicious program or malicious code does. So user B might be unaware of this, because it's a malicious code and it's inserting the data which is only accessible for user B. And since the table P is now given it the permission to insert data to table P is given to or granted to user B, now this malicious code which is being executed with the authorization of user B can insert data to table P. So the table P is originally created from user A, so user A can do whatever the particular user wants. So now this original data, which was only accessible for user B, is exposed to a user different from user B. So this sort of approach is called a covered channel. So here, user A, this is user A, and this is user B. And user A creates a table and then grants privilege to insert data. And then the user A inserts a malicious piece of code to the user B's program, and then what it does is it will extract some of the data which is only accessible for user B and insert them into a table here in the bottom. So now the table is created by user A, and user A is the owner. So user A has the full access, and now the data will be exposed. So that is a problem in discretionary access control. Rather, we would say it's a kind of a limitation. So the DAC, the data owner has full control over granting permissions, which can lead an unauthorized access if the owner makes a mistake or grants permission too broadly. So this introduces a security risk because users can either unintentionally or maliciously grant access to others without considering broader security policies. So that is some sort of a problem or maybe limitation in discretionary access control. Role-based access control, or RBAC. RBAC simplifies access control by assigning users to roles. So these roles are pretty generic and simplifies the responsibilities and duties user can perform. Therefore, we would say that roles are often too broad and do not account for the sensitivity of data. If a user has the role of manager, as an example, these manager roles might have access to more data than necessary because it's a kind of a generic role, but each and every user which is assigned to these roles, this manager role, might not need all of these data which is accessible through this manager role, right? So we cannot control the sensitivity of data through these roles. Then what we call here is need to know basis. So that is kind of a security principle. So we should only allow the users to access data based on the need to know basis. So that is a problem in role-based access control. We call that we cannot control the granularity in sensitive environments. So each and every user should have very specific authorizations when they are accessing critical or maybe sensitive data. In such environment, through the role-based access control, we cannot control these sensitivity or the granularity in sensitive environments. So another problem or limitation in discretionary access control is once access is granted, let's say with admin privilege or maybe with grant privilege, these users can freely propagate permission to others. So it has no restriction. If you give that grant privilege or maybe admin privilege, you can't control. Users can freely transfer these privileges to others. So this can lead to insider threats where trusted users share sensitive data with unauthorized individuals. And role-based access control, again, RBAC does not inherently enforce separation of duties or prevent conflicts of interest unless we explicitly design these roles into the role structure. So separation of duties and maybe preventing conflict of interest. So such requirements are not inherently included in typical role-based access control environment. So if the environment specifically has not been decided or defined with such separation of duties or maybe preventing conflict of interest. So such requirements are not specifically built into roles, then we will be having a problem. So that problem is users may potentially hold multiple roles that might be having conflicts. So this might lead to abuse or security breaches. So just imagine a user who both approves and audits transactions. So if such roles are assigned to the same user, then that might be a huge problem. So it's a risk. So that's why we call that we cannot control such conflict of interest roles through role-based access control model in a typical implementation. There might be very specific cases that we can restrict such access, but typically that is not the case. In both discretionary access control and role-based access control, users with administrative privileges can modify access control. So this might potentially granting themselves more access than they should have. On the other hand, both DAC and RBAC allow some flexibility in how access control are implemented, which can lead to inconsistent application of security policies, especially in large or complex environments. So when it comes to mandatory access control, before we start it, we need to know that discretionary access control has been the traditional access control mechanism most of the cases. Even if we implement role-based access control, discretionary access control is inbuilt into that implementation. So DAC has been there, and it's quite prevalent as an access control mechanism. When it comes to mandatory access control, so it adds an additional layer of security. So we are not going to totally avoid discretionary access control, but we will be adding mandatory access control as an extra layer of protection or extra layer of security by classifying objects and users based on security levels. So I will highlight this. So classifying objects and users based on security levels. So that is the distinct part here in mandatory access control. Multi-level security is required in government, military, and intelligence applications, which means when the data and the resources is having the higher level of criticality or maybe higher level of sensitivity. When we are dealing with highly confidential or highly private data, right? So when we need to protect them with extra layer of security, we may tend to go into mandatory access control, where it specifically introduces different levels of security, right? So that is the uniqueness here in mandatory access control. So we will be seeing different levels or hierarchical sensitivity levels when it accessing data. So some relational database management systems do not facilitate mandatory access control requirements. Let's see some of the characteristics of mandatory access control. We call it mandatory access control is non-discretionary. So in discretionary, you know what is the idea of being discretionary. So that is basically there is an owner for each and every resource, and the owner decides how this object or how this resource should be exposed or how it should be accessed. Non-discretionary means it is not subject to the discretion or decision of individual users or resource owners. So owners and the users who created resources cannot decide who and what permissions will be authorized to other users. So the access control is non-discretionary. So the owners cannot decide how this should be accessed. And instead, it is security policy oriented. We call it's non-discretionary. Users cannot decide what is happening. Instead, security policies will be there to decide what should be the mechanism which data should be exposed and what should be the access mechanism for the data. And third, we call it need to know principle. So users are only granted access to data if they have a legitimate or if they have an actual requirement to access it. So based on their security clearance and the classification level of the data, we will be allowing them to access. So the access requirements or the data exposure will be prominently or completely decided or based on need to know principle. So we can specifically restrict access to certain data based on this need to know principle, right? So the key idea is MAC, or the mandatory access control, is non-discretionary, which means the owners or the users will not be able to decide how this data will be exposed, right? And instead, this access or maybe the exposure of data will be determined based on a more central manner, more policy oriented, right? So policies will decide how the data should be exposed, and the data will be exposed based on need to know principle. And then we call, because of the nature of mandatory access control, we call it, it's a rigid model. It's rigid model, right? So it does not have the flexibility that we saw in previous two models. So we know that in discretionary access control, it's quite flexible. If I want, I create the data object, I created the resources, then if I want, I can grant whatever the privilege, right, for each and every user. And it's very we can say that it's fine-grained access control can be given with this discretionary access control. And role-based access control, again, we can decide certain privileges, and we can introduce an abstract role model, and these models or these roles will be assigned to users, where users will inherit all the privileges of these roles that govern. So it's quite generic, and all the privileges that is encapsulated with a role will be given to a user when the user is assigned to a role. So that is pretty broad and generic. And when it comes to mandatory access control, it does not follow those two models. Instead, it's quite rigid because it's completely security policy based, right? So see, whatever the rule, whatever the mechanism, security policies have introduced, that will decide how a user can access data. Access control are applied uniformly across the system, irrespective of the users. So it does not care the designation of the user, maybe the other attributes. All of these attributes are immaterial when it comes to Mac, because it centrally implements these security policies and controls access control. High security, it is because of this strict and stringent nature of the implementation, and the term mandatory underscores the fact that security controls are not optional and must be adhered to without exception. So the idea mandatory is it's very rigid. So once the access control is defined, you have no way to evade it. So you will be completely under control by those access control rules. So DAC and RBAC and MAC, how shall we compare it? So DAC is user-centric. We know that it's user-centric. Owners has the full control, and DAC has more control, more flexible, right? Less scalable because of this. When we are having large number of users, large number of resources, we will not be able to easily configure these access control requirements because of this user-centric nature. And these problems are handled to a certain extent by role-based access control. It's role-centric and it's scalable. But when we want more control, maybe having more strict access control, and when we are dealing with more sensitive and more critical data, we may enforce mandatory access control as an extra layer of security, where it brings a rigid framework to control and govern the data, where it prevents accessing data without the proper authorization. So as a side note, I will introduce this. MAC takes a more stringent and centralized approach to access control. It emphasizes the need to know principle and enforces strict separation and isolation of data based on classification levels. So users have limited control over access permissions, and security policies are typically defined at a higher level. In contrast, discretionary access control and role-based access control provide more flexibility and user autonomy, allowing resource owners and role administrators to manage access permissions. These models are often used in commercial and enterprise settings, where security requirements may be less strict and users need more control over their resources. So, need of multi-level security models. Why do we need it? We call that need for multi-level security exists in organization and bodies where they are handling very sensitive data or maybe critical data compared to typical information systems in enterprises. So just imagine government secrets, maybe military secrets, intelligence applications. So such environments require very strict access control mechanism to ensure the security of the data that they are handling. So at the other end, they need to control these accesses through or in a more central manner, and they need this central control over the access. And also, organizational policies are enforced through a centralized access control management mechanisms. So, mandatory access control is a good match in this case. So let's imagine, or let's assume a scenario like we may need entry access control. A military organization needs to establish a highly secure communication system to exchange classified information among different units and personnel. So this is a quite common requirement when it comes to governments and military. So to start with, mandatory access control, what it does is it introduces security labels. All data and users are assigned security labels or security clearances. So that is how it starts with. There are security labels. Data is classified into different levels. So based on the sensitivity or based on the level of criticalness, uh, data or the resources are classified into different levels. As an example, we can take unclassified, confidential, secret, and top secret. A very simple case or very simple hierarchy. So there will be confidential data, there will be unclassified data, there will be secret data, and there will be top secret data. So there is a order, there is a hierarchy of sensitivity. Similarly, users are assigned clearance levels that correspond to these classification levels. So each and every user will have a clearance level. Access control policies. The organization defines strict access control policies that dictate who can access data at different classification levels. So we can say that only users with top secret clearance can access top secret data. So that is a very simple uh, access control policy rule. So what we said as need to know principle is users are uh, granted access only to the information that is essential for their specific goal. So when they have legitimate requirement, they will be given, otherwise will not grant the permission. So here we have given an example. A communications officer may have access to secret communication channels, but not top secret channels unless their job requires. security policies and clearances are centrally administered and managed by security administrators. So these policy decisions are taken in a more central manner, and hence we can implement them with this mandatory access control and this more central control over the access. So let's assume a typical case, or maybe as an example, a typical security levels. So we may use, right, throughout this lesson, we will be using this security levels as a sample. So this is an example security levels, right? So we have 4 levels in this case: top secret, secret, confidential, and unclassified. So top secret data, it is the most sensitive data in the organization. So we say that it has the higher sensitivity and more dominance over other levels. And next, secret, confidential, and unclassified. So the level of sensitivity increases. So that is what we show here. So when it comes to multi-level security model, right, there is a model that is being followed in such multi-level security models. So that conceptual model is called Bell-LaPadula, BLP model, right? So this Bell-LaPadula, so it's a model that is being followed through these multi-level security frameworks. So it controls the flow of information. So this BLP model, so Bell-LaPadula model, so that is referred as BLP in certain context, right? So it's proposed a lattice-based model. So lattice is an abstract structure. It's an abstract structure studied in the mathematical subdisciplines of order theory and abstract algebra. So we don't actually really need to know about the lattice, but this is these lattice-based models. Since BLP is a lattice-based model, it will be quite helpful to represent these ideas. So BLP is a set of principles that brings or that controls the flow of information in multi-level security models. So it's a way of controlling information flow. So in BLP, it has two main principles, right? Two main principles. One is called simple security property, and the second one is called star property, right? So these two properties control the flow of information in multi-level security models. So more information about the BLP model. So it was introduced by David Elliott Bell and Leonard J. LaPadula in 1976. So they together introduced this idea to control the flow of information. These properties should be adhered, so it will ensure that in multi-level security requirement, the information that flows through the framework is controlled based on multi-level requirements. So they developed this model while working on a project for the United States Department of Defense to secure classified information in computer systems. So lattice structure. So this sort of structures or this sort of graphs are called lattice structures, right? So you see here is a lattice structure. So these lattice structures have been used for implementing or maybe visualizing and understanding mandatory access policies, mandatory access control policies. So you would see that these models organize. So these lattice structures organize security levels and permissions into mathematical structure called lattice. In such a lattice, each point or each node here you see. So these are called nodes. These are nodes. All these nodes or points represent, or each node or each point represents a particular security classification or clearance level. And the relationship between these points define what access is allowed. What access is allowed. So if you look at there are two levels of sensitivity that is being referred in this diagram, right? So the upper layer of this lattice is about top secret data, right? So all these four nodes are associated with top secret, and the possible data objects or the resources is, so this C is a one resource, air and C is another possible combination. Air is another option, and not having any resource at this top secret level is another level. So this lattice shows all the possible combinations of resources and their sensitivity levels, right? So this lattice shows all possible cases, right? And their superiority. So if you look at top secret and empty resource is inferior to top secret C. So that's why this arrow is in this direction, right? So arrowhead shows that which is superior. And top secret C is inferior to top secret A and C, which means if we are given top secret ARC clearance, right? So if we are assigned this clearance, this particular clearance, then we can access any resource, any data which is inferior to that. So if I am given this top secret ARC, then I will be able to refer all the inferior resources, top secret C, top secret empty, top secret AR, right? And at the same time, secret level data or the resources are also inferior to me. So I will be able to access all the inferior data, right? So that is the idea, or that is how we are going to represent these concepts in lattice structure. In a lattice model, objects are labeled with their sensitivity levels. So you saw earlier in unclassified, secret, top secret. These are security labels, sensitivity levels. Levels correspond to the risk associated with release of the information. So the levels, these security or the sensitivity levels correspond to the risk associated with the exposure of the information. It is not sufficient to use only sensitivity levels to classify objects if one wants to comply with need to know principle. So when we want to bring this need to know principle into our MAC framework, so these levels of sensitivity is not enough. So we need some other aspect in this model framework. So access to information should only be granted if it is necessary to perform one's role. So that is what we call need to know principle. And compartments are used to handle this decomposition of information. So every object is associated with the set of compartments. As an example, crypto, nuclear, biological, recon science. Likewise, there can be many compartments. An object associated with cryptonuclear may be accessed only by subjects who need to know about the cryptography and nuclear weapons. So those who really want to know about crypto and nuclear will have this access. So that is what we call need to know principle. So in a typical lattice model, a label is a pair of sensitivity level and set of compartments. Sensitivity level, compartment. So this is a typical label. So this is the sensitivity level and this is the compartment. Right? So a label in a typical that is structure, a label comes with two components. One is the sensitivity level and the other one is the compartment. Similarly, users are also labeled according to their security clearance. So users are also labeled. Given two labels, L1 and L2. Let's say L1 is having sensitivity level S1 and compartment C1, and label 2L2 is having sensitivity level 2 and compartment 2. So in this case, we say that L1 is inferior to L2, right? L1 is inferior to L2. So that is because L1 is no more restrictive than L2, right? So L1 is either inferior or equivalent to L2 such that S1 is the sensitivity level, is if S1 is less sensitive, right, than S2. And C1 is the compartment of the first label, and C1 is a subset of C2, right? So if that happens, we call that L1 is L1 is inferior to L2, or maybe L2 is superior to L1. So this is a lattice model or the lattice structure. So you see that two sensitivity levels, secret and top secret, and each level there are several database objects like nuclear, crypto, and based on these two database resources, it shows different labels that we can create, all the labels that we can create in this case. So top secret layer is the upper layer and secret layer is the lower layer. So in a label, this part is called the sensitivity level. Top secret, secret, right? So these are sensitivity. And this is called the compartment, right? Compartment. And when we consider the entire unit, we call it label. So these are labels. So this is entirely, this is a label. These are labels. So then let's see what BLP says in this context. BLP, right? Bella Padula. BLP model specifies three properties. So initially, I said that I just introduced two properties, but actually it specifies three properties. First property is simple security property. We name it as simple security property, and it is about the read operations in this environment where mandatory access control is being enforced, how read operations are governed. Second property is called star property, right? So it is about write operations. In an environment where mandatory access control is enforced, how write operations should be performed. So why we are specifically looking at these two? Because with the multi-level security, we have to ensure that the strictness of this resources or the strictness of data should be ensured through write and read operations. So these two properties specifically looking at read and write aspects. And the third property is any access must respect a provided access matrix. So access matrix is something like this. So let's see what does simple security property is about. What is simple security property in Bell-LaPadula model, right? So simple security property says a subject S is not allowed to read access. Allowed to read access means basically cannot read to an object O unless classification level of subject S is greater than or equivalent to the classification level of O, right? So I will repeat it. Any subject S is not allowed to read an object O unless the subject's classification level, that is what we refer here as class S. Subject's classification level should be greater than or equivalent to object's classification level, right? So what does it mean? It means nobody should be allowed to read a resource unless the user is having superior or equivalent classification level compared to the resource the user is going to read, right? So let's say we are having a hierarchy of sensitive level like this, of secret, confidential, and unclassified. So if this is the case, a subject with, let's say, secret classification. So subject is here. So subject is in the secret level, is not allowed to read access to an object unless subject's classification level is greater than or equivalent to classification level of object O. So this subject will be allowed to read any resource which is equivalent or lower in this hierarchy, right? So any resource which is in unclassified, any resource in confidential level, or any resource in secret level will be allowed to read by the subject or the user. However, the user will not be allowed to read resource which is higher than the user's security level. So that is the idea. A user cannot read beyond the security clearance level that she is assigned, right? So the user will not be allowed to read anything beyond his or her clearance level. So in simple terms, we call it no read up. So the reading up is prohibited. Reading down allowed, right? So this simple security property is about reading, and it says that nobody can read beyond the security clearance level that she is assigned. No read up. Then the second property is star property. It is about writing. So the star property, it says a subject S is not allowed to write an object O unless the classification of subject S is less than or equivalent to classification of object O. Right? I will repeat it. A subject S is not allowed to write an object O unless the classification level of S is inferior to the classification level of O. So the user's clearance level should be inferior to the data which is being written, right? So what does it mean? A user cannot write below the security clearance level that she is assigned. So users will not be allowed to write data or create resources in a lower level, right? So in the hierarchy, right? So let's say the hierarchy, this user is in S. So this user cannot write data to the lower levels. So this is prohibited. The user can only write higher levels, right? So we call it no write down. The user cannot write below the security clearance level that she is assigned, right? So you might be wondering why it allows to write, why it does not allow to lower levels, because that is the more, rather I would say that you may feel like that, okay, why don't we allow someone to make the data available for the lower levels rather than writing the upper level? The reason is, so if we allow writing to lower levels, that might leak data, right? So we need to keep in mind that we are dealing with sensitive data. So if we allow leaking such data, that will be detrimental. So we should ensure that no data will be written to a lower level than the user's clearance level, right? So if we allow this, it will create an opportunity to a user to expose the data into a lower level users. But if we do not allow a user to write anything beyond or anything below the user's clearance level, that will ensure that nobody can share the data to users in lower levels. So that is star property. So a system may not be secure even if it always confirms the two Bell-LaPadula properties correctly. A secure system must additionally guard against covered channels. So by implementing BLP properties will not ensure the security that requires complete insight. A secure system must additionally guard against covered channels as well. Introducing MAC to relational database management systems is pretty challenging, because there are certain problems that we would encounter once we introduce uh, mandatory access control or maybe multi-level security in relational databases. So we'll be discussing them separately. Multi-level relational model is an extension to the relational model. So we can theoretically we can introduce multi-level relational model, right? MLR, multi-level relational model, assumes different tuples in the same relation may have different access class, right? So that is pretty obvious. So if we are dealing with relational database which is enabled with multi-level security, then in the same table there can be multiple rows in different clearance level or security sensitivity levels, right? So one row might be in unclassified level and another row might be in a confidential level. Another row, a third row might be in a secret, right? So likewise, there can be a lot of different data in different clearance levels. So when it comes to relational databases, so we know that data are organized into tables. Tables keep this data, and if you take a single table or relation, data are organized as rows and columns, right? In a table or relation, primary key of a table is to uniquely identify each and every row in the table. So each table typically has a primary key which uniquely identifies each row in the table. So primary key ensures that each record in table is unique and identifiable. So it ensures that data duplication will not happen with the tables. And then relationships between tables are established through keys. You know that a foreign key in one table references the primary key of another table. So it creates a relationship between two tables. These relationships enable the representation of complex data structures and facilitate data integrity and consistency. Normalization in relational model, it supports normalization, a process used to minimize redundancy and dependency in database schemas. Normalization involves breaking down large tables into smaller, more manageable, and it ensures that data is stored in a way that reduces anomalies and inconsistencies. So in again relational model, SQL or the structured query language, it is used for data access and manipulation. It's a standardized language for defining, querying, and manipulating relational databases. SQL provides a powerful set of commands and syntax for performing operations such as selecting, inserting, updating, and deleting. So ACID properties, relational databases adhere to ACID properties. We did this in the first lecture, I guess. ACID properties, atomicity, consistency, isolation, and durability. That is what we define as ACID. So it ensures that database transactions are executed reliably and maintain data integrity. So this is a typical relational model: tables, primary keys, relationships, SQL, normalization, and ACID properties. So when we bring multi-level security into relational model, we call it, that model is multi-level relational model. So it is basically combination, or it's a hybrid model which combines relational database model with multi-level security requirements. You know that in a multi-level security, there are different access classes. So when we bring this multi-level security to relational model, these access classes can be assigned to relations or maybe individual tuples or maybe individual columns relate attributes or individual data element of a tuple in a relation. So likewise, there are different ways or different levels of granular that we can define. A relation is partitioned into different security partitions. So the same relation might contain data in different security or sensitivity levels. Therefore, we can say that a relation can be partitioned into different security partitions. Security levels in a relation is a concern because it can contain many different levels. In standard relational model, right? Not the multi-level relational model. This is a standard relational model. Data stored in relations which have well-defined mathematical properties. Each relation has two parts, right? So if you take typical relational database management system, in each relation we see two parts. The first one is a state invariant relation scheme. So in this relation scheme R, where each AI is an attribute over some domain, which is a set of values, right? So relation scheme is the definition of that relation, right? So this A1, A2 up until AN is the attributes, right? So as an example, if we take student relation, right? Student relation, there can be many attributes starting from student's index number, right? Index number, and maybe the name, date of birth, address, telephone number, right? So all these are different attributes. So each of these attributes is over some domain, right? So what's the domain? And possible values that it can have, right? So if you take date of birth, we know that it's a date type attribute. So its domain is basically about dates. And if we take index number, right? So it's again, there are number of possible values it can have. So that is the domain. And that is the first part of a typical relation. State invariant relation scheme. Relation scheme is about the definition of the relation. And it is state invariant because it doesn't matter what data is stored in that relation, right? Irrespective of the data it stores, its definition is fixed. That is why we call it, it is a state invariant relation scheme. The second part of this relational model, each relation has two parts. First part is relation scheme. Second part is state dependent relation over R, which is a set of distinct tuples of the form A1 to AN, where each element AI is a value in domain D. So First one is state invariant relation scheme. So it doesn't matter what data is stored, its scheme is unchanged. Second part is state dependent relation. So second part is about the data it has stored, right? So time to time, the data might be different. That's why we call it state dependent, right? So it should contain the number of attributes which is defined in the relation scheme and the corresponding values, right? So state dependent relation which consists of distinct tuples in the form A1 to AN. So a multi-level relation is characterized in two conceptual components. So previously it is about the standard relation, and when it comes to multi-level relation 2 is characterized in two conceptual components. So that 2 has two components. One is a state invariant relation schema, similar to the previous case. Second component is a set of state dependent relation instances. Right? So in the standard relation model, we call it state dependent relation, right? So the relation is dependent state of the relation, state dependent. So time to time the data will be changed, therefore we call it relation is depend on the data. But here we call it is a state dependent relation instances. So there can be instances of relation. So what are these instances? So let's look at a multi-level state invariant relation schema R can be represented as, so you remember here, state invariant relation scheme was defined as R, A1, A2, AN. They are the attributes, right? So index number, name, address, telephone number, likewise many attributes. So when it comes to multi-level relational model, it defines its relation schema as A1 C1, A2 C2, A3 C3, AN CN, and DC. So what are these A1 C1, right? So A's given here is they are attributes similar to the previous case. Index number, name, telephone number, address, likewise all these A's are about the attributes. Then what is C? What are these C? These C's, they are the classification attributes associated with attribute A. So for each attribute, what is the classification? Whether it is top secret, whether it is confidential, whether it is secret, whether it is unclassified, likewise. So this C is about the classification. For each attribute value, there will be an associated classification level, right? So let's say in a standard relational model, let's say our our relation is like this. Let's say this is index number, and then let's say name. Address, telephone, this is the standard relation. So you may have different index numbers. Like let's say someone has index number like 22, 0, 5, 8, like twice, like name, uh, Sam, likewise there can be many rows. So that is the ordinary or standard relation. But when it comes to multi-level relation, addition to these attributes, there will be so this is the classification of index, right? So this is the classification of name. This is the classification of address. This is the classification of telephone number, right? So each of these data items will have its own classification levels. Like this might be confidential. This index number might be confidential. Name might be confidential. Address might be secret, right? So the telephone number might be secret in another student, right? So the next student here, index number, it is possible that the second student might have a different clearance level or the classification level, right? So this might be, let's say, you, unclassified, name, right? Unclassified, address might be unclassified, telephone number may be confidential. So likewise, each data item that you are storing in this relation will have its own classification level. So this defines state invariant relation schema, or it defines all these attributes and their corresponding classification levels as C1, C2, C3, and Cn. So this TC is added to the attribute of a relation R. So we add another attribute TC. It is a classification for each tuple as a whole. So if we take a tuple as a whole, what is the classification level? What is the classification level if we consider the tuple as a whole? So we know that in this particular row, there are multiple levels involved with confidential, security. So if we take this tuple, if we take this row as a whole, what is the label that we are going to use? So that should be marked here. Then that is the first component of multi-level relation. Second is a set of state-dependent relation instances. A set of state-dependent relation instances. So this term is important, relation instances. Set of state-dependent, depend on the state, right? So what does it mean? Depending on the data that we hold in the table, in the relation, right? State will be different, so state dependent. Relation instances. So we will have different instances of the same relation based on the security classification of the data. Because if we take this relation, if this is the relation, so what we are going to show to a confidential level user, or maybe user with confidential level, will be different from the version of the relation that we are going to show to a user with secret clearance level. So we are showing two different versions. So we call it two different instances are available for two types of clearance levels, right? So if we think of 4 types of clearance levels, we may have 4 different types of instances. So we will have data in different instances, a set of state-dependent relation instances over R for each access class in the access class lattice. Each instance RC is composed of distinct tuples of them of the form where AI is a value in domain D, whatever the value. CI is the access class for AI, the corresponding access class. TC is the access class of the tuple determined as the least upper bound of CI. And so this should be subscript N, right? A1, C1, AN, CN, and EC. Classification attributes cannot assume null values. So all these C1, C2, C3, C4, Cn values cannot be null because there should be a classification level, right? So it cannot be null. Each attribute classification CI provides a finer security classification for each attribute value AI within a tuple T. The value of TC in each tuple T is the highest of all attribute classification values. CI within T. So then we introduce a term called apparent key. The apparent key of a multi-level relation is the set of attributes that would have formed the primary key in a regular relation. So in a multi-level relational model, what refers as apparent key is the primary key if the same relation was in the standard relational model, right? So let's take this example again. If this relation was in a standard or the ordinary regular relational model, then we know that this classification columns C1, CI, C, and CA, all these C and TC column. So these are not available if the same data was presented as a relation in a typical standard relational model. So in standard relational model, we don't have classification levels. So in such a context, in such a database model, what would be the primary key, right? So let's say in such a situation, we can easily take index number as a primary key because index number is a unique attribute for each and every student. Then index number is the primary key in such environment. So when we come to the multi-level relational model, we call that key or that attribute as apparent key, not the primary key. So in a multi-level relation, primary key, we cannot take the same key as primary key because there can be two tuples, two rows with the same apparent key because of these security classification levels, because the same entity might be having two different representations, two different instances of the same entity of data might be in two different security clearance levels. So a user with one security clearance would see a different picture than the user with a different clearance level that sees in the data item. Therefore, we can't use the same key that we used as primary key in typical relational model as the primary key in relational model, right? As a result of BLP properties, right? As a result of BLP properties, subjects, or more familiar way, we can say users, having different clearances, see different versions of a multi-level relation. That is what I said. Users with different clearance levels would see different instances of multi-level relation. So it is not the same version of the relation that is seen by a user in top secret level and a user with unclassified level. A user having a clearance at and access class C sees only the data which lies at class O below. Element T, AI, in a tuple T is visible in instances at access class T, C, I, or higher. So what does it mean? If we take any tuple T and its attribute AI, right? So tuple T's attribute AI, a particular attribute, is visible in instances at access class of the classification level of that attribute or higher, right? So the data attribute value will appear in instances where the classification level is CI or higher, right? So if there is a table, let's say this is a table, there are many rows, many columns, and its classification level, right? Another attribute, its classification level, another attribute, its classification level, another attribute, and its classification level. So let's say the value stored here is X, and its classification level is confidential, right? So this is the tuple T. This is attribute AI, and this is CI, right? So if you take any tuple T and its attribute value AI, which is X here, is visible in instances at access class TCI. TCI is confidential level or higher. So what it means is this X will appear. This X will appear in instances of this relation where it is instance is level confidential or higher, right? So you know that our level of the hierarchy of this top secret, confidential, unclassified, right? For each level, there will be an instance of this relation. So if this relation is R, right? So there will be R top secret. Yes. Similarly, there will be R secret, a different instance. There will be R confidential. There will be R unclassified. Right? So there will be 4 instances of this same relation because it's in multi-level relational model, right? So what it says is this X will appear in confidential level, right? So where its X values level of classification. So it will appear in instances RC or higher. Higher instances are here, RS, R secret, R top secret, right? So in all these 3 versions, 3 instances, X will appear and X will not appear here. In this instance, RU, X will not appear. So typically, this X is replaced by a null value in an instance at a lower accessor. So what it means is, if we take the instance RU, in that RU, this X will appear as a null value because its classification level does not allow it to appear in a lower level than itself, right? So that is what we mean here, visibility of data elements. Right, as an example, let's say multi-level relation, a typical multi-level relation. The classification attribute values next to each attribute value, right? So columns, ID, name, salary, job performance, and the tuple classification. So ID1 in unclassified level, the name of the ID1 holder, Amal, and again, it's unclassified. Salary of Amal is secret value. Job performance fair. It's again secret. And the highest level of classification that we see in this row or the tuple is S. So we give TC as S. The second one is its ID is 2. Name is Amal. Salary 120. Right? Job performance good. Yes. Third, its ID is 3, but its classification level is C, right? Different. And the name is Nimal. Again, Nimal's name is confidential. Salary is confidential. Job performance is poor. Again, it's a secret, right? Assume that the attribute ID is the apparent key. So in this case, we have to take that right. So assume that the attribute ID is the apparent key, which means if we bring this same data, the relation into a standard relational model, that we would not see these classification attributes. So we will bring these columns ID, name, salary, job performance only with their data. So in such a context, ID will be the primary key. Therefore, we refer this column as apparent key in this multi-level relation. So let's say the result that a user with security clearance S secret, right? S is secret, would see for the query. So a user with security clearance S now issue this select asterisk from employee query, which means extracting everything from the table employee. So that will bring all the data in the table, right? So you see that this is the original table, right? So all the data stored in this table is either in level S, classification level S, or below, right? S or below. Therefore, the user will be able to see all the data. However, let's say a user with clearance level C, confidential, now confidential user is attempting to issue this SQL query and extract data. In that case, that user will not see all those data which was in the original table as secret. So these are secret data, right? Secret data will be hidden from the user because the user in a lower level, right? So these values will be set to null. And case 3, a user with security clearance level U, unclassified. That user will see most of the data as null, and also the user will see only 2 rows. A row is not visible to this user. Why? If you take this original table, in the original table, the row number 3 completely contains data which is not in the unclassified level or lower. So all the data here are in a higher level than the U, right? So therefore, that will not appear. So these are 3 instances of the same relation, right? So this is the instance that available for users with clearance S. This is for C. This is for U. 3 different instances. So a relation may have instances at different access classes. So we saw that a relation may have different instances. An instance of a relation that is at class C contains all data that are visible to subject at level C. Right? So it contains all data whose access classes are dominated by C. Dominated by C means either the data are in level C or lower than C, right? So that is how the level is dominated. Either the data is in level C or lower. All elements with access classes higher than C or incomparable are masked by null. So all the data which is in a higher level or maybe incomparable are masked by null value. So the values will be set to null. Sometimes to avoid signaling channels, fictitious values can be used. So in a more specific cases, like when you set it to null values, the user might suspect, right? So let's say this user will be in a suspicion that why are these null values, which means there are some values which I cannot see, which means it is having some more sensitive data which I cannot access. So that will indicate the user that there are some high sensitive data. So in order to, if we really want to avoid that signaling, we may include fictitious values when we are setting it to null values. So those are implementation details. There can be implementations which set these fictitious values, and there can be implementations which it doesn't include fictitious values. Instead, it set the data into null. Then we look at polyinstantiation, which is a kind of a different concept, right? So what is polyinstantiation in multi-level relations? There might be necessity to store two or more tuples at different classification levels with same value for the apparent key, right? So here, this is what I mentioned earlier when I am introducing the term apparent key. There might be necessity to store two or more tuples at different classification levels with the same value for the apparent key. With same apparent key, there can be different different rows with different classification levels, right? So such scenarios are called polyinstantiation. Just imagine in the same example that we took earlier, student table, student relation. So index number is the primary key. So when the relation is brought to multi-level relational model, that index number become apparent key, right? So in a typical or standard relational model, there cannot be two rows with the same primary key, right? Let's say there is a index number 2000, which is a student who follows Master of Cybersecurity degree program. Index number is 2000. So there cannot be two rows with the same index number in a typical standard relational model. But when it comes to multi-level relational model, there can be multiple rows with index number 2000, where these rows are having different classification levels, right? So the row with index 2000 might be in top secret classification, and there might be another row with index number 2000 but in confidential level, right? So why do we want to keep multiple rows with the same apparent key? So there are two possible cases. A user with low clearance inserts data into a field which already contains data at higher or incomparable level, right? Let's say a user with low clearance, which means, let's say, an unclassified user is attempting to insert a row that has index number 2000, right? So that will be inserted as an unclassified data item. However, at the time of the user inserting this data, the user doesn't know that there is a same data item, same tuple, which is already stored by a higher level user. So it might be in confidential level, right? So it is not visible to the unclassified user because the unclassified user is lower level. So he or she can't see it. So the unclassified user is now attempting to insert the data, and it will allow. Otherwise, the user will be given some indication that there is a higher sensitive data which has the same apparent key, right? So it should not be allowed. Then this will allow keeping the both rows in the relation with different classification. So that is the first case. Second case is a user with high clearance inserts data in a field which already contains data at a lower level, right? A user with higher clearance now attempting to insert data in a field which already contains data at lower level, right? So in that case too, it will create multiple rows, right? So several tuples can have the same apparent key value, but have different attribute values for users at different clearance levels. This is similar to the notion of having multiple versions in the database that represent the same real-world object. So same student, same real-world object here means the same student is represented in two different security levels. So we are keeping two rows. So that's why we call it polyinstantiation. Polyinstantiation. So again, we are bringing these two possible cases, two types of polyinstantiation. One is called invisible polyinstantiation. So the user with low clearance insert data into a field which already contains data at higher or incomparable level. So that version is called invisible polyinstantiation. And the second is visible polyinstantiation. A user with high clearance inserts data in a field which already contains data at a lower level. So higher users cannot write data to lower levels. That is a key policy in PLP model. You cannot write down. Therefore, higher users cannot write or cannot insert data into the lower levels. So it will create a different tuple in different classification level. So in invisible polyinstantiation, which means lower level user is attempting to insert data, however, there exists the same apparent key in a higher level. In that case, one option is reject the insertion. So if we reject it, it gives an indication of primary key or the apparent key existence, right? So that is not as good as we expect. Another option in this scenario is replacing the existing tuple at a higher level with new tuple at lower level. So that compromises the data integrity, and that is also not a good option. So the option 3 is the more feasible option. Insert the new tuple at lower level without modifying the existing tuple at the higher level. So we are keeping both tuples. So we call it polyinstantiation. So let's say this is the original table, and a user with clearance level U is the lowest clearance level, attempt to insert a tuple given here, right? So when the user attempting to insert this tuple, there exists a tuple in the original table with the same apparent key, right? Apparent key 3 exists, but it is in confidential level, right? The user cannot see it because user is in level U. Right? Therefore, user is unaware that there exists a tuple with the same apparent key. So what happens is user will be allowed to insert the data, which creates polyinstantiation, which means creating or keeping two tuples with the same apparent key. This is the first row, and this is the second row with the same apparent key, right? So this is called invisible polyinstantiation because the user doesn't see these both versions. Invisible polyinstantiation. Second version is visible polyinstantiation, where higher level user attempting to write to the database where the same apparent key exists in a lower level. So again, we can reject it when the higher level user is attempting to insert. We can reject it and saying that the apparent key exists. The problem is user is attempting to insert data because the user really wants to insert. So in that case, user cannot achieve the required objective, rejecting. Option 2 is replace the existing tuple at lower level with the new tuple being inserted at the higher level. So then again, it's a sort of a data integrity issue, and at the same time, it indicates that tuple has been overwritten. So when the lower level user come back and look at the data which was earlier in the lower level, now not available, so the user knows, okay, somebody has made a modification where the tuple is now in a higher sensitivity level. So that is also not that good. So more feasible option is keeping the multiple levels in multiple tuples. Insert a new tuple at high level without modifying the existing tuple at the lower level. So what happens here? So this is the original table, original relation. A user with clearance level S, now a user with higher clearance level is attempting to insert a tuple, this one, right? However, this tuple is already with the same apparent key exists. However, already existing data is in a lower level, right? So this ID is now in unclassified level. Name Amal is unclassified. So they are in a lower level, right? Now this user who attempts to insert is in a higher level. So in this case, what happens is the multi-level relational model keep both tuples, this one and that one, right? So this is called visible polyinstantiation because this higher level user sees both tuples, right? It is visible. So that's why we call it visible polyinstantiation. Right. So that's all about mandatory access control here today. And we will have a second part of mandatory access control, which we look at polyinstantiation in detail and its challenges and how we can maintain the integrity while keeping all these multiple versions of the same tuple, right? So that will be looked at next time, and today we will end this at this point. So if you have questions, anything to clarify, please let me know. Okay, it seems there are no questions. I will end the session, and thank you very much for joining, and good night to all of you.